So the main goal of this lesson today is to look at centripetal acceleration and centripetal force. So when we talk about centripetal, this term centripetal actually means center-seeking or center-loving, depending on how you want to define that. And so since an object is changing directions in uniform circular motion, its velocity is not constant. If the velocity is not constant, that means the velocity is changing, and if the velocity is changing, there must be a way to define the acceleration for that object, because the object must be accelerating. And in fact, in this case, the acceleration relates to this change in direction, or how quickly this thing is changing directions. So what is the magnitude of this acceleration? What can I do to solve for this? It actually happens to be a fairly straightforward equation to solve for the acceleration of an object in uniform circular motion. I'm not going to go through the derivation of this equation. There are a couple different ways you can derive this equation. If you're interested in that derivation, ask me and we can go through it together. I don't think that it's really all that valuable that you know how this equation gets derived, just that you know that this equation works to calculate the acceleration of an object moving in a circle. And it really only depends upon two things: the speed of an object and its radius of its circle that it's traveling in. It's worth pointing out that the direction of acceleration is always toward the center of the circle. You might ask, why is that? Well, that's because if it was either in a direction that pointed maybe slightly in the direction of motion or slightly in the opposite direction of motion, what would happen is that the speed of the object would have to speed up or slow down. It has to be perpendicular to the direction the object is traveling so that it doesn't change the speed of the object. What this means is the net force on the object has to be perpendicular to the direction the object is traveling. Well, the direction that's perpendicular is toward the center of the circle. So in order to calculate centripetal acceleration, I would do the speed the object is moving and square it and divide it by r. If you actually do this calculation and think about it in terms of units, you do get an appropriate units for acceleration. If you have meters per second and you're squaring it, you get meters squared over second squared. Divide it by another meters and you get meters per second squared acceleration. So here we go. Let's look at centripetal acceleration. If this object is moving up at this point, the acceleration must be perpendicular. Again, we said it must be perpendicular because the direction of, or the way in which the velocity is changing direction is toward the center of the circle. And as this continues to move around the circle, we can continue this motion, that the acceleration always points toward the center of the circle. It has to be perpendicular to the velocity so it doesn't change the velocity. And well, it has to be pointing in the direction that the motion is changing. You can almost think about this like in projectile motion being at the top of your motion of a projectile, that your velocity is horizontal, yet your acceleration is vertical at that point. In projectile motion, that acceleration does not change your horizontal velocity in any way, shape, or form. And that's really the exact same thing that's happening here. All the acceleration is doing in this case, it doesn't change the speed, it simply changes the direction of travel. So let's look at an example problem. Let's go back to our race car that we had before. We have this race car traveling around this circular track, radius of 350 meters in 45 seconds, and I want to know what is the magnitude of centripetal acceleration on the race car. It's going to be v squared over r. We know how to calculate v from before, that it's 2 pi r over period. And so we can actually figure out what v is. That's example problem 1 from the last lesson, 48.9 meters per second. And we could plug it in and we get 6.082 meters per second squared, which really is actually a pretty normal and reasonable acceleration. This would be something a little bit less than the acceleration due to gravity. The second concept question I have is, let's say we're swinging a rock by a string in this circle. Let's just assume we're looking at this from the top down and this is a horizontal circle, so we don't need to worry about gravity at all. We're just looking at how this thing is moving in a horizontal direction. And let's say when the rock gets to point A, the string breaks. Which of these three paths does the rock take? Well, let's think about this for a second. If the string breaks, well, then there's nothing to keep this rock moving in a circle. You've eliminated that force. Well, if that is the only force that acts on an object, and in fact, in circular motion, the force that gets directed toward the center of the circle is the net force acting on the object, well, the net force is now 0. The object should move in a constant direction, or the direction of the object shouldn't change. Well, only one of these three paths has a direction that doesn't change, and that's path 2. Now, I know some of you probably want to pick path 3 thinking, but it was moving in a circle beforehand. Shouldn't maintain some of that circle motion? And the answer to that is no, it doesn't. The reason why it doesn't is if you remove that force, if you remove the string, you no longer have the force that's causing it to move in the circle in the first place. And so the net force is 0 by Newton's first law, moves in a constant direction, constant speed, velocity remains constant. That's direction 2. So let's look at how we can calculate this force that we call centripetal force. And centripetal force is really pretty easy to calculate once we know centripetal acceleration. If we use Newton's second law, force is equal to mass times acceleration. If acceleration is v squared over r, centripetal force is m times v squared over r. And it's also worth pointing out that centripetal force points toward the center of the circle. It actually causes the object to continue to move in the circle because it's changing the direction of the object toward the center of the circle. Let's go back to example problem 2 and 1, where we have this race car traveling around this circular track of a radius of 350 meters in 45 seconds. And let's say I want to determine the magnitude of centripetal force on the car if its mass is 1,500 kilograms. So you have mv squared over r as the centripetal force. I know how to calculate v. We've done that already twice in example problem 1 and example problem 2. V is 48.9 meters per second. And we can plug it into that formula, and I get 10,200 newtons. I could also probably take the answer to 5.2, what was it, like 6.72 or 6.82 meters per second squared, and multiply it by 1,500, and I would get the same answer, the 10,200. So that's kind of a quick example of centripetal force that we have for a problem that we might want to deal with. Now, what are some applications for this? And we'll get into this a lot more in future lessons. There's many situations that can be modeled as uniform circular motion. 3 of the big ones that I can think of off the top of my head are a circular orbit due to gravity, a car moving around a curve, and an object being swung in a circle by a rope, a string, a chain, something else. If we use our knowledge of forces, if we reach back to Unit 3, Newton's laws and forces, we can determine what's going on in these various situations and then begin to determine something about the circle. Maybe how fast it moves in a circle, or what radius of circle we need, or what is the force that has to be acting on the object to move in this circle. Really depends upon what we're actually looking for in that problem. So in the next few lessons, we'll start to look at some applications of this motion and how we begin to describe these various applications. The first application that I'll look at is the circular orbit due to gravity, and what are some things that come out of our equations for uniform circular motion.